Section 4.2 is going to be about binomial distributions. So we have to start out by talking about what a binomial experiment is. There are many requirements in order for an experiment to be considered binomial. First, there has to be a fixed number of trials. So I have to be running this experiment 75 times or 83 times, but I can't just have an unlimited number of trials, and it's got to be fixed. Each trial can only have 2 outcomes. So generally, the way that we take care of that is to consider each trial either a success or a failure. So I either got a 3 or I didn't get a 3, or I drew the Queen of Hearts or I didn't draw the Queen of Hearts. The outcomes must be independent for each trial. So the outcome of one trial cannot affect the probability of the next trial. The probability of success must remain the same for each trial. And then the random variable, which is x, is going to represent the number of successes. So we have a formula for binomial probability. Binomial probability, the formula is P of x equals NCX times P to the x times Q to the n minus x. So I'm going to talk about what each part of this formula means. P, of course, means probability. X is the number of successes. And that's the same here, 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 and here. So X is always the number of successes. N is the number of trials. So N is the number of trials here and the number of trials there. P is the probability of success. Q is the probability of failure. And you find Q by knowing that P plus Q has to equal 1. And then if you look at this N minus X, if N is the number of trials and X is the number of successes, then N minus X is the number of failures. So basically, we're going to be doing the number of trials, C, that's the combinations, number of successes, then times the probability of success raised to the number of successes, times the probability of failure raised to the number of failures. So let's look at an example. So let's say that I get out my good old candy jar and it has 2 peppermint, 1 spearmint, 3 root beer candies, 1 butterscotch, 1 strawberry, 2 cinnamon. So these are the candies in my candy jar. So what's going to happen with my experiment is with replacement, I will draw 5 candies. So I'm going to draw a candy, put it back, 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 draw a candy, put it back. So I'm going to do that 5 times. And I want to know what is the probability that I get strawberry, which is my favorite, 3 times. So this is a binomial experiment because it's going to meet all of these requirements, as we'll see. There is a fixed number of trials. So the number of trials is how many times I'm going to draw candies. So that is 5. So this is my number of trials. Each trial can have only 2 outcomes, success or failure. So in this case, a success is that I draw a strawberry candy. A failure is that I draw any other flavor. So those are my 2 outcomes, strawberry or not strawberry. The outcomes must be independent because it's with replacement. That makes them independent trials. The probability of success must remain the same for each trial. So the probability of success, that's what we use the letter P for in our formula. So probability of success, I have 1 strawberry, and I have 2, 3, 4, 5, 6, 7, 8, 9, 10 candies. So the probability of success is 1 in 10, and that will remain the same each time because I'm putting my candies back. And then the random variable x represents the number of successes. So I want to know what's the probability I get strawberry 3 times. So this is my x. X is 3, which is the number of successes. So to figure out my binomial probability, I want the probability that I get 3 strawberry candies. So P3, the number of successes is 3. Then I have the number of trials, C, the number of successes. There are 5 trials. I want 3 successes. So 5, C3. And then I'm going to take the probability of success raised to the power of the number of successes. Probability of success was 1/10. The number of successes was 3. And then I need the probability of failure. Well, I know P plus Q has to equal 1. P is 1/10. So Q has to be 9/10. So the probability for failure is 9 out of 10. So then I'm going to take the probability of failure raised to the number of failures. So 9/10 to the power of, well, if I had 3 successes in 5 trials, then I will have 2 failures. So then I'm just going to go in my calculator. If you remember where, I think it's in math. Yep, math probability, NCR. So I need 5C3. So that is 10 times 1/10 to the power of 3 times 9/10 to the power of 2. And that gives me 0.0081. So the probability that I will get 3 strawberry candies when I draw 5 is 0.81%. Let's look at some more examples determining whether something's a binomial probability experiment or not, and then working through some. Here I have, I'm not going to cut this page apart, by the way. Determine whether the experiment is a binomial experiment. If it is, specify the values of n, p, q, and list the possible values of the random variable x. If it is not, explain why. So, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So, since the outcome of one surgery is not going to affect the outcome of the next surgery, we can say that these are independent. So that's one of our requirements. So it is independent. Another requirement is we have a fixed number of trials. The doctor is going to perform the procedure on 8 patients. So that's our number of trials, which is fixed. So x is going to equal 8. N is going to equal 8, number of trials. Another requirement is that each trial can have only 2 outcomes, which are success and failure. So that is also true. The probability of success has to remain the same. That is this right here. That is p. So p would be 0.85. So we've met all of our requirements for binomial. So it is binomial. And then we need to identify n, which we said was 8. P is 0.85. Q would be 1 minus 0.85, so Q would be 0.15. And the possible values of x, well, x is going to represent the number of successful surgeries. So out of 8 surgeries, x could be 0, 1, 2, 3, 4, 5, 6, 7, or 8. So we could have anywhere between 0 and 8 successful surgeries. Number 2, a jar contains 5 red marbles, 9 blue, and 6 green. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. So if we go through, fixed number of trials is the first one. So this would be our number of trials. We randomly select 3 marbles. So that is our n would be 3. Each trial can have only 2 outcomes, success or failure. So success would be a red marble, failure would be not red, so that requirement is met. Outcomes must be independent. Here we have without replacement. If I don't replace the marbles, then the probability the second time I draw is different from the first. So these are dependent trials, which means it is not binomial because the trials have to be independent. Okay, let's do this one. Determine whether the experiment is binomial. Oh, we're doing the same thing, so I'm not going to read the directions. You take a multiple choice quiz that consists of 10 questions. Each question has 4 possible answers, only one of which is correct. To complete the quiz, you randomly guess the answer to each question, and the random variable represents the number of correct answers. So, do we have a fixed number of trials? Yes. Our number of trials is 10, so n would be 10. Next requirement, each trial can have only 2 outcomes, success and failure. So in this case, success would mean that we guess the correct answer. Failure would be that we get the incorrect answer. So we have that going. The outcomes must be independent. That's true because I'm going to guess randomly each question, so each trial would be an independent outcome. The probability of success must remain the same for each trial. So each question has 4 answers, only one of which is correct. So the probability of success would be 1 in 4, so 0.25, meaning the probability of failure would be 0.75 on each outcome. And our random variable x has to represent the number of successes. So our possible values of x could be anywhere between 0, and 10. Okay. So I want to ask you a question about this test. The question I want to ask you is, what is the probability that you get an A? So in order to get an A, then I would need to get either 9 questions or 10 questions, and I guess I wanted that in one parenthesis. The probability that I get 9 or 10 questions. Sorry about that. So remember that the formula for the ORs was that I would take the probability of 9 plus the probability of 10 minus the probability that it is both. But since I can't get both 9 and 10, that value is going to be 0, so I don't need to worry about it. The probability that I would get 9 correct is going to be, I'm going to use that binomial formula. So the probability of 9 would be n C9. So 10 trials, C9 successes, and then times the probability of success, which is 0.25, raised to the number of successes, which would be 9, times the probability of failure, 0.75, raised to the number of failures, which would be 1. And then I have to do the same thing for 10 successes. So 10C10 times 0.25. Now I have 10 successes times 0.75, and I have 0 failures. So then I would want to be using my calculator here. So math probability 10C9. And then I can just go straight across here, 0.25 to the 9, and then 0.75 to the first. That is a very small number. And then I am going to also do 10C10 times 0.25 to the 10th times 0.75 to the 0. Also a very small number. I need to add those two numbers together, and that gives me a still small number. That means I need to move the decimal 5 places to the left, meaning I would have 4 zeros and then 29563903881. So what would be the probability that if I randomly guess on a multiple choice test that has 4 options and 10 questions that I get an A would be 0.003% chance that I would get an A. Now I could also go back and figure out what's the probability that I would get, that I would pass, like say get a 70. But then I'd have to do P7 plus P8 plus P9 plus P10, and that sounds like a lot of work. So I'm going to skip that for now. Okay, rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. So this is going to be binomial. I mean, it tells us it is, but we can tell it is because we want to know the probability of exactly 2 successes out of 3 trials when the trials are independent and there are only 2 outcomes and the probability of success remains constant. So it just fits all of those requirements. So I want to know what is N, what is X, what is P, what is Q. So in this case, it's performed on 3 patients, so that's our N is 3. We want the probability that it's successful on 2 patients, so that's X is the number of successes. Probability of success is 0.9, And the probability of failure then would be 0.1. So the probability that we would have exactly 2 successes is NCX, so 3C2, and then times the probability of success, 0.9, raised to the power of the number of successes, which is 2, times the probability of failure, which is 0.1, raised to the power of the number of failures, which would be 1. So we go through our math steps, our calculator steps. 3C2 times 0.9 squared times 0.1 to the first. That gives us 0.243. So there is a 24.3% chance that the surgery will be successful on exactly 2 patients, no more and no less. Let's look at a binomial distribution. Binomial distribution. So what I'm going to do is I'm going to say that I know the probability of the number of successes for each of, no, I'm going to go up to five trials. Okay, I'm stumbling. Give me a moment to collect my brain. A binomial distribution. Along the horizontal axis is going to have the number of successes. So it would keep going all the way till we get to however many successes there are. So then the horizontal axis is x, which represents the number of successes. So if I have 10 trials, then it will go from 0 all the way up to 10 in the number of trials. Then along the vertical axis, we're going to have probability, like we did in our other probability distributions. So if I had, let's just say my binomial distribution looks like this. So theoretically, let's say that n is 5, and this is what my probability distribution looks like. Then my binomial distribution, P of 2 would be equal to the height of the 2's bar. But if I wanted the probability of fewer than 2, then I would need to add up the probability of 0 plus the probability of 1. So then I would be adding the height of the 0 bar to the height of the 1 bar. It would not include the height of the 2 bar because I wanted fewer than 2. So we can actually do this in our calculator. This right here, this 2, would be exactly 2 successes. So if you have a binomial experiment and you want to figure out the probability of exactly 2 successes, you can do this in your calculator by going to the DISTR menu. Now that menu, you've probably never ever even noticed it on there, is the second for the vars button. So it's the second feature for the vars deal. So we would go to the distribution menu, and we're going to choose A, which is Binomial PDF. So we choose all the way down to A, Binomial PDF. And then what we're going to tell it is the number of trials, the probability of success, the number of successes, and then it's going to go from there. So let's say I have, the one that we just did a second ago, we had 3 trials. The probability of success was 0.9, and we wanted the number of trials to be 2. So on my operating system, this is what it looks like, and then I hit enter. Your operating system may look different. You may actually have to type it in those parentheses. So you may have to type in on your calculator the value for n and then put a comma, the value for p and then put a comma, and then the value for x. So remember, n was the number of trials, p was the probability of success, and x was the number of successes. So if you have to type it in, then your screen should look like that. And then you hit enter, and it will tell you the value is 0.243. So you can see that you got the same value using your calculator that we got on when we did it by hand. Now, on the test and on your homework, unless it specifically says use your calculator to figure this out, you need to show me the work for doing that kind of stuff. Now, you can definitely check it with your calculator. I'm totally okay with that, but I want you to know how to do it using the formulas. Now, if I wanted to know the probability of fewer than 2 successes, then I would use a different menu choice. So if I want to know X or fewer successes, then I go to the same menu, DISTR menu, but I'm going to choose option B, which is Binomial Cdf. That's cumulative distribution something. And then I put in NPX. So this is going to add up like the probability of 0 plus the probability of 1 plus the probability of 2 up until the probability of whatever X value you put. So let's say, for example, if I wanted the probability of 75 or fewer, let's say our number of trials is 100, our probability of success is 0.25. So if I want 75 or fewer, because remember it's going to add up 0, 1, 2, 3, all the way up to X. So if I'm including 75, I will use X equals 75. But if I want the probability of fewer than 75, then I don't want to include 75, so I would use X equals 74. So let me show you what that looks like on the calculator. Go to the DISTR menu. You have to scroll all the way down to B. And in this case, my number of trials, which is 100. My probability of success, 0.25. And my X value, I'll use 75. Enter. Oh, that probability is 1. Maybe I should use a smaller number. Let's go 7. 7 or fewer, fewer than 7. If it's 7 or fewer, then I use X equals 7. If it's fewer than 7, then I would use X equals 6. I didn't realize that was going to come out to be that. So we'll try that again. Second, distribute, go down to B. Now my X value is going to be 7. Okay. Now that's a really small number. So it's 5 zeros, and then 29889239005. Now if I use x equals 6, arrow down to B, that's 6 zeros. Okay. So you can see that it does make a difference what value you use, depending if you want to include that value or you don't want to include that value, then you need to make some alterations when you put it in your calculator. So just be aware of that difference. Okay, let's look at constructing a binomial distribution. This, I'm going to have to do the work for this on a separate piece of paper because I don't have room for it. So we'll come back and look at this back and forth with a piece of paper. So in a survey, U.S. adults were asked to identify what devices they use to access social media. The results are shown in the figure. 7 adults who participated in the survey are randomly selected and asked whether they use a cell phone to access social media. Construct a binomial probability distribution for the number of adults who say yes. So we are just talking about using our cell phone to access social media, and that would be here on cell phone. So let's make sure it's a binomial distribution for sure. So we've got to go through those requirements that we started with. One of the requirements was that there was a fixed number of trials. So fixed number of trials. It says 7 adults who participated are randomly selected. So yes, there's a fixed number of trials. It is 7. We need to know if there is only 2 outcomes. Are there only 2 outcomes? So the question is, do you use a cell phone to access social media? So the responses are either yes or no. So there are 2 outcomes. Next is the outcomes must be independent. They are independent because the first person's answer isn't going to change the second person's answer. The next one is the probability of success constant? We are going to base our probability of saying yes on this chart right here. So the probability of success is going to be that 46, because 46% of people said they do access social media on their cell phone. So that's going to be the probability for success. It will be 0.46. And then the last one is the random variable x is the number of successes. So x could possibly be anywhere from 0 to 7. So yes, it is binomial. So we're going to go ahead and create a binomial distribution that we can make that kind of histogram looking chart. So we need to know what is the probability of 0 successes, the probability of 1, 2, 3, 4, 5, 6, and 7 successes, so that we can make our probability distribution histogram. So we're going to have 0, 1, 2, 3, 4, 5, 6, and 7. And this is going to be, X represents the number of adults who respond yes. So the chart is going to show, do you use your cell phone to access social media? We are going to have probability over here. And the way that we're going to get those probabilities is by figuring them out using binomial distribution. So remember that formula for binomial distribution. Probability of a specific number of successes is NCX times the probability of success to the number of successes times the probability of failure to the number of failures. So this is going to be quite a bit of figuring. I'm going to write out a couple of them in here, and then I will pause my video as I'm recording, and you can fill out the rest of them and then check to see that you know how to create all of those. And then we'll do a couple in our calculator and do the same thing. So the probability of 0 successes, the number of trials was 7, so it would be 7C0. And then P was the probability of success, which was 0.46. So 0.46 to the number of successes, which is 0. And then the probability of failure is 1 minus 0.46, so 0.54 to the number of failures. If there are 0 successes, then there would be 7 failures. And then we would put that in our calculator. So we go to the math menu, probability, 7C0 times 0.46 to the 0, not to the 10, times 0.54 to the 7. And that is 0.0134. And I'll just do another random one. We'll do this one here. So the probability of 4 successes would be NC4, so 7C4 times the probability of success, which was 0.46, to the number of successes, which is 4. Then the probability of failure, 0.54. And the number of failures would be 7 minus 4, so 3. So I can actually just do second entry and then go in and edit my values. So 7C4 and then 0.46 to the 4th and 0.54 to the 3rd. And that gives me 0.246. I'll round that to 0.2468. Okay, so I'm going to pause my video and I am going to fill in all the rest of these values and get all of these values. You do the same. So go ahead and pause the video now, fill this in, and then when you start to play it again, we'll check what you got versus what I got. Okay, so take a moment, maybe pause the video again, check to see that we have the same probabilities for each number of successes before we go to put them on our probability distribution. So I'm assuming that you have paused and come back and everything's hunky-dory, and we're going to then graph these. So I need to go at least up to 0.3 probably. So I'll just go by, I'll just go by these. So 0.1, 0.2, 0.3. And I'm going to put the bars for this histogram to the height of the probability. So 0.01 is pretty low. This is 0.05, this bar. So 0.01 would just be tiny. The probability for 1 is 0.08. For 2 people to say yes, the probability is 0.20, just a tiny bit above 0.20. The probability of 3 people saying yes, they use their cell phone to access social media, is 0.29. The probability of exactly 4 people saying yes is 0.25, roughly, by rounding. Probability of 5 people saying yes, 0.13. The probability of 6 people saying yes would be 0.04. And the probability of 7 people saying yes would be really, that's almost 0. So now I have my probability distribution for the number of people who said yes when we asked 7 adults if they use their cell phone to access social media. So we can use this distribution to answer some questions, such as what would be the probability of exactly 5 people saying yes? So the probability that 5 say yes, probability that exactly 5 say yes. So that's the probability of 5. And we already know the answer to that is 0.1261. And on our distribution, it is the height of this bar right here, 0.1261. But what if I wanted to know the probability that fewer than 5 say yes? So the probability of fewer than 5, I can actually find this 2 ways. So one way would be to figure out the probability that 4 said yes, plus 3 said yes, plus 2 said yes, plus 1 said yes, plus 0 said yes, because that would be fewer than 5. So that would be this bar, this bar, this bar, this bar, this bar, and I would have to add all those up. So when I do that, if I add up, let's see, 0.2468, 0.2897, 0.2040, 0.0798, and 0.0134, that gives me 0.8337. But if you notice that I've had to add up 5 bars to get that number, there is actually another way to do that. Notice that I have 8 bars total, and I used 5 of them to figure that out. Now, the entire probability, if I added all of those up, the total probability should equal 1. So if I wanted to know the probability of 0, 1, 2, 3, 4, 5, 6, and 7, I add those all up, and that would equal 1, which means this number should be equal to 1 minus this, this, and this. So the other way that I could do this would be to do 1 minus the probability of 5, 6, and 7, which would be these bars. So if I add up 5, 6, and 7, 0.1261, 0.0358, 0.0044, I get 0.1663, and I do 1 minus that number, gives me 0.8337. You may remember this from at some point earlier we talked about the complement of events, that the probability of an event plus the probability of its complement would equal 1. We can use that concept to shorten out what we do with these binomial distributions. There is also a binomial table that you can use to look things up. So if your assignment tells you to look up a binomial probability using a table, then you would go to that table and look up the number of trials, n, and then within that number of trials, how many successes. And it has limited values for the probability of success. So that's why we don't use it that much, because we can just figure it out using the formula. So here, they want you to look up, it says 10% of workers commute to their jobs by carpooling. You randomly select 8 workers, so that's your n is 8. What is the probability that exactly 4 of them carpool to work? So that's your x. X is 8. P is 0.1, because that's the probability of success. So in this table, we would go to where n is 8, x is 4, and p is 0.1. And you follow along in that table, and we get 0.005. So the probability that we get 8 who say they carpool to work would be 0.005 or 0.5%. Now notice this little mabobber thing right here. It says because 0.005 is less than 0.05 or 5%, so 0.5% is less than 5%. This can be considered an unusual event, because remember, if a probability is less than 5%, it's considered unusual. So on our answers to the number of people who said yes to using their cell phone, if I asked 7 people, what would be an unusual number of yeses? Unusual number of yeses when I ask 7 people would be anything that's less than 5%. So that would be this one, which is 1%. That one's 7%, and that's higher, higher, higher. This one, that's 3.5%, and this one, that's 0.0044%. So an unusual number of yeses would be 0, 6, or 7. Let's make one more binomial distribution just for practice. And then we're going to take a little bit more notes and then do one more example. And we'll be done. Okay. About 60% of cancer survivors are age 65 years and older. You randomly select 6 cancer survivors and ask them whether they are age 65 years and older. Construct a probability distribution for the random variable x, then graph it. So the probability of success would be 0.6. Probability of failure would be 0.4. So I'm going to need to figure out, n is 6. So I'm going to need to figure out p of 0, 1, 2, 3, 4, 5, and 6. So we'll have to do all of that formula work that we had done before. So like for P of 4, that would be 6 trials, choose 4 successes. Probability of success is 0.6. Number of successes is 4. Probability of failure is 0.4. Number of failures is 2. So we put that in the calculator. C4 times 0.6 goodness, to the 4th times 0.4 squared is 0.31104. Okay, fill in the rest of that and then check back with me in a moment. There are all my figures. Then when I go to create my probability distribution X is going to equal the number of people who say they are over 65. Well, excuse me, are 65 or older. Up here, I will have my probability. My values for X are from 0 to 6. And I'll put my probabilities over here based on these bar heights. So this one is practically 0, 0.04, 0.14, 0.2765, so about 0.28, 0.31, a little bit higher than that, and 0.18, so 0.19 roughly, and then 0.04. So that's what this distribution would look like. Now, what would be considered an unusual number? Unusual number who would say they are 65 and older. Remember, that's anything that's below 5% probability. So that would be 0 of them, 1 of them, or 6 of them. We're going to skip this example, and I'm going to go on to a piece of notebook paper and give you just a little bit of notes about these distributions. So one thing that we can tell from the probability of success is what kind of skew we have. So the options are for p to be equal to 0.5, for p to be less than 0.5, and for p to be greater than 0.5. So if we look at the distributions that we've just made, we made this one, and a moment ago we made this one. So on this particular probability distribution, our probability was 0.46, probability for success. So probability was less than 0.5. On this one, p was 0.6, so p was greater than 0.5. And if we look at our tails, you can kind of tell on this one that the left tail is longer. So this gives us a left skewed graph. And on this one, here's the top of it. So our right tail is longer. This was pretty close to 0.5, so it's a little harder to tell. But this gives us a right skewed graph. So when our probability of success is less than 0.5, we will have a right skewed distribution. When our probability of success is greater than 0.5, we will have a left skewed distribution. And when our probability of success is equal to 0.5, we are going to have a symmetrical distribution. Now, one cool thing that we can do with a binomial distribution is we can find the mean super easy. For a binomial distribution, the mean is going to be mu equals n times p. Variance sigma squared is equal to n times p times q. And then, of course, standard deviation is going to be the square root of sigma squared, or the square root of n times p times q. So let's go back and look at this San Francisco example. In San Francisco, about 44% of the days are clear. Find the mean, variance, and standard deviation for the number of clear days during the month of May. Interpret the results and determine any unusual events. So let's see what our N, P, and Q are. So we're looking at the month of May. The month of May has 31 days, so that's going to be N. It says 44% of the days are clear. So the probability of it being a clear day would be 0.44, which means the probability of failure, not being clear, is 0.56. So to find our mean, we just do N times P. So that is going to be 31 times 0.44, which is 13.64. To find our variance, we take N times P times Q. So that's 31 times 0.44 times 0.56. So that is 7.6384. Standard deviation will be the square root of variance. So square root of 7.6384, which will be 2.7376547. Okay. So the mean, we're going to interpret the results. So in San Francisco, I can't spell, San Francisco, the mean number of clear days in May is 13.6, and the standard deviation is 2.7 days. Now they ask us this question of, well, they don't ask. Yeah, they do. Determine any unusual events. I thought maybe I made that question up, but I did not. What would be considered unusual? Remember back when we talked about distributions, we said what would be considered unusual would be more than 2 standard deviations from the mean. So we would need to take our mean and add 2 standard deviations, and take our mean and subtract 2 standard deviations. So if we take 13.6 and add 2 times 2.7, take 13.6 and subtract 2 times 2.7, that would give me 19 here. And when I subtract 2 standard deviations, that gives me 8.2. So what I can say is it would be unusual to have fewer than 8.2 clear days, or more than 19 clear days in San Francisco in May.